Good morning, good afternoon, and good evening, everyone around the world. My name is Hemendra Khakkar, and I am the Licensing Business Director for Wood Technology and Consulting Business in our Houston office. Houston office is our center of excellence for heavy oils processing technologies and operation tech services. Today, we are planning to discuss the basics of SDA solvent deasphalting technology and how the whole process fits into the residue conversion complex, as well as the whole refinery in terms of product routing, optimization, and economics. We will also see how it is going through Renaissance period and why SDA is such a great tool to improve the refining margins and also reduce the fuel oil and low value bottom stream production simultaneously, both by killing both birds at the same time. So before we discuss this SDA, I would like to introduce you to the wood process technology portfolio. So of course, we have changed our name to Wood, but our customers know us as Foster Wheeler for more than 100 years. And we are the leading licensor of residue upgrading technologies for a long time. Our major technology focus is the bottom of the barrel technologies, including delayed coking, visc breaking, thermal cracking, and solvent deasphalting, of course. We are also leading licensor of hydrogen SMR technology and sulfur recovery complexes, including the modified Klaus process, tail gas treating, amine treating, etc. And we also have a Vestar technology in our portfolio, which is great at efficiently converting solid fuels like petroleum coke into SNG, synthetic natural gas, which ultimately can produce petrochemicals or fuels. And we know petrochemicals is the talk of the town nowadays. So this is also technology which is getting great importance in the market. Let us look at the high-level overview of how SDA works. It is a very simple and elegant process. SDA is a physical separation process, just like the distillation. But it separates not by the boiling point, but by the molecular weight and the molecular type. The process works by adding a light paraffin solvent to the feed. Typically, the solvents are C3, C4, or C5 propane, butane, pentane, which causes the precipitation of asphaltenes and resins from the feed. Now, then both the extract and raffinate phases are separated out because of the density differences. And you can see from this nice picture how the asphaltenes and resin molecules, along with the HPNA, heavy polynuclear aromatics components, can be visualized by the color scale from heavy vacuum resid on the left to the de-asphalted oil, relatively cleaner products on the right side based on different contaminant levels. And we'll see how it affects the DO quality and the contaminants level based on the different process parameters. So we just saw that fundamentally it is the asphaltene and resins precipitating, which is the heart of the process. What are the asphaltenes and resins? They are actually the core of the process, and that itself defines how the SDA process works. Asphaltene molecules are defined as insoluble in C5, but soluble in C7. C7 is heptane, of course, while resins are the molecule that precipitates out in C5 solvent, but not in C7. And as indicated, as you can see from the bottom chart, asphaltenes have the highest molecular weight, of course, and polarity and aromaticity in the residues for obvious reasons. And aromatics, resins, and asphaltenes all form a continuum of molecules with, when you increase the molecular weight, aromaticity, and heteroatom components or contents. So asphaltenes, to a large extent, if you look at this, one thing is very clear, that asphaltenes to a large extent and resins also to some extent contain most of the nickel, vanadium, and corn carbon, and also a substantial amount of sulfur and nitrogen compounds. This is a very nice illustration of SDA chemistry. If you look at the molecular level, the feed to the SDA, the resid, basically atmospheric or vacuum resid, the molecules are part of the colloidal system, which you can see on the left. This contains, as you can see, continuous oil phase, oil hydrocarbon phase, and then asphaltenes, you can see, which are kind of a suspension, is held in suspension by aromatic resins. Now, when you add the solvent, any paraffinic solvent, what happens is the oil phase, the hydrocarbon phase, dissolves the lower molecular weight, lighter components. So what happens is, of course, it gets higher hydrogen content, lighter component, and it gets lower density than the resins molecules. And so now asphaltene clusters start precipitating until the equilibrium achieves. And so we see higher and higher concentration of asphaltenes in that phase. And that's how we get the concentration in the pitch. So if we look at the contaminant distribution of the different components, what we consider as a contaminants like nickel, vanadium, corn carbon, sulfur, nitrogen, etc., into the feed, we can understand how it separates into the extract and raffinate phases. And of course, I mean, extract phases is the phase where we are separating out the solvent with the components which are desirable, and the raffinate is the pitch phase. In this chart, we are seeing the pilot plant data for various very, very difficult to process crudes throughout the globe in terms of sulfur, nitrogen, corn carbon, nickel, vanadium, all that good stuff. And if you look on the picture on the top left, that's the sulfur. And there is a clear difference. You can see the sulfur is distributed roughly linearly with the boiling point. And when you compare all the different curves for all different crudes, irrespective of the crude origin, it holds true. And then comparing all the other contaminants like nickel, vanadium, and CCR, they are concentrated in the back end of the vacuum resid. And of course, it gets heavier and it gets worse with the heavy tail, as you can see here. Now, how does this distribution we just saw impact the SDA process? So obviously, I mean, based on what we saw, it is going to be very selective to the metals, CCR, but at the same time, to the lesser extent, to sulfur and nitrogen because it was linear throughout the boiling point. So that's the advantage, right? We can leverage that for CCR and metals, which is, of course, the contaminants we want to get rid of in our desirable product, deasphalted oil. So there are various ways to interpret this graph. And this is, of course, the main interpretation, the whole process, how SDA works. But the most obvious one is the careful balance of DAO, deasphalted oil, yield and quality in terms of contaminants. On the plot, as you go on the right, by increasing the lift of DAO, obviously you are seeing more and more contaminants like nickel vanadium in a non-linear fashion. But after a certain lift, you are seeing exponential increase depending on the crude type and other design parameters. And that is, of course, because of the separation efficiency and the equilibrium limitations. The right-hand side, so if you look at the plot, the right-hand side shows the 100 volume percent in the DAO is the same percent as the volume percent of feed. So that's how you can interpret the plot as well. The most important part to remember as a rule of thumb for the whole SDA process is there is a limitation to how much maximum SDA lift you can achieve in the whole process. And it's relatively simple. So let me try to explain. The maximum limit of the SDA lift depends on how much C5 insoluble components you have in the resid feed if you use the C5 solvent. So this is an example for C5 solvent and C5 insoluble, but it holds true, of course, for other carbon numbers, C6 and C7 as well. So the bottom line, for example, if you have a 40% C5 insoluble in your resid feed, your maximum possible ideal lift would be 60%. So that's how you can really look at very high level the SDA, what is achievable and what is possible. So we saw the fundamentals and the chemistry of the SDA process, and that's what I just wanted to share before we go into the commercial process. So based on this fundamental research and a lot of the pilot plant testing, SDA was commercialized by Foster Wheeler in 1960s. And of course, it has been growing and improving ever since. The SDA process is commercialized, and now it has been jointly licensed now by Wood and UOP jointly. And UOP is part of the UOP Honeywell group, which also licenses other technologies. So our joint SDA process, which is ideal for maximizing the recovery of quality DAO, which is also optimized and offered for 2 product and 3 product applications. And we'll see those flow schemes in later slides. The Wood technology design is an advanced counter-current design using the structured packing, which minimize the entrainment of contaminants in the DAO stream. And we also minimize the utility cost and operating cost by utilizing the supercritical solvent recovery, which is key for the better DAO quality and obviously the lower operating cost. And also the SDA process has been optimized for heat integration with pinch technology for each application. And as we saw, there are typically two products: lighter product, which is the DAO, which is the desirable product for the catalytic conversion downstream, and the heavier product, which is a pitch, which is typically suitable for a coker or a boiler for power, etc. And we'll see those details, configurations, and detailed routing scenarios. So basically, the process is very simple and relatively low severity at low temperature and low pressures relative to the other acid conversion units. And also, as we'll see, it has a very small count of pots and pans with a very small plot space. So quite attractive for the refineries which are struggling with a plot space and the space constraints. So this is the simplified flow scheme for two products, for DAO as well as the pitch. If you look at the flow diagram, starting with the left, so vacuum resid or any resid feed is mixed with some fraction of pre-dilution solvent, typically 0.5 to 1 volume %, and feed is cooled and routed to the extractor. The bulk of the solvent is routed to the bottom of the extractor where of course the separation process occurs and the pitch phase forms like we saw before. The pitch is withdrawn, heated, and stripped to recover the entrained solvent. The upper section is essentially a coalescing section. The bulk of the solvent along with the DAO is recovered overhead. And the mixed solvent DAO solution is heated and routed to the DAO separator where the solvent is recovered, and the bottom's DAO with the solvent is heated and routed to the stripper, where again solvent is recovered and cooled and reused in the extractor, recycled and recovered from the strippers. So as you can see, it's a very, very simple flow scheme with extractor at the heart. You are adding the solvent, separating out the extract and raffinate phases, and recovering the solvent. That's about it. Here is a little more complex scheme for three products, which is to say to recover additional intermediate resin product. So here, to recover the resin product, there will be two additional vessels, resin settler and a resin stripper. So comparing the flow scheme, I mean, there are, and also look at the pots and pans, what kind of internals are there in the resin settler and the DO separator? They are exactly the same as the extractor. So all three vessels will have packed beds for separation efficiency. How about the supercritical separation, where it occurs? It only occurs in a DO separator section. And one key part of the flow is also to reduce the equipment sizing, etc. The feed which is sent to the resin extractor only contains DO and resin and not the full content. So again, it's this process is optimized to recover additional resin products. And there are many other product applications for the resin we'll see in the later slides, along with obviously recovering a stream which can be, which is used to recover more useful components like the DAO and reduce the pitch product. We have looked at the simplified flow scheme. Now let us review the SDA design parameters very briefly. So the whole SDA process, if you think about it, is based on one parameter, which is called SDA Hildebrand solubility parameters. This parameter delta, which is a function of heat of vaporization, temperature, and the solvent volume. So this describes the whole SDA separation behavior. With the design parameters, pressure, temperature, type of solvent, and the solvent ratio to the feed. So let us look at each parameter, how it affects the process. The first is pressure. So how does it impact it? Increasing the pressure, increasing the solvent strength, and obviously increases the yields of DAO and the recovery. Look at the temperature impact. This is an interesting plot, and you can see the impact of both C4 and C5 solvents with respect to temperature on the DO yield. And directionally and qualitatively, both solvents has the same influence for obvious reasons. As you can see, reducing the temperature fundamentally increases the solvent strength and increasing the DO yield. But remember, of course, there is a temperature limit for the process because we are using a supercritical flow regime and thermodynamics for the DO extraction and the solvent recovery. So we have to operate in a limited temperature window because we would like to operate at a lower temperature, but also we have to stay away from the critical point. So these are very critical parameters, and depending on the feed quality, etc., we have to consider for the design. Of course, solvent selection is very important for the design to meet the quality for DO and the yields objectives. These are very simplified illustration. As you can see, as a rule of thumb, you have a DO yields gets higher with heavier solvent. Of course, with a compromise of somewhat higher contaminants. There is optimization between the two like we saw before. So when you look at the high level picture for your application, how do you decide this, what solvent to use for your SD application is typically SDA process has been used widely for a long time in the lube production, right? For the group 1 and group 2 lube production. You can't do much with the group 3 because you need hydroprocessing, but for group 1 and group 2, there is a huge installed capacity for the SDA to make the group 2, where in lubes we know that the quality constraints are very stringent. So for the DO quality maintenance and also to meet the objectives, we have to use the C3 propane solvent. Even though it will meet the quality, but you will have a limited yields. On the other hand, where you can live with higher contaminants, but you have to maximize the DO yields, you use the heavier solvent like C5 or even heavier. And the example could be, let's say you are looking at a very heavy crude or tar sands, like, for example, Venezuela, Orinoco Belt, heavy crudes, Colombian or Canadian tar sands in the bitumen. And if you want to use the SDA to produce the synthetic crude for those material, you are producing a synthetic crude and not the typical SDA DAO. So that means you can live with the higher contaminants, you have less constraint, and that means you are maximizing the synthetic crude for the pipeline. That means you need to use something heavier to maximize the yield, like C5, C6. So this is a great example of the solvent selection and how you can look at a bigger picture. The another design parameter is solvent to oil ratio. Oil means the feed, vacuum resid or atmospheric resid. So typical solvent to oil ratio for SDA design ranges from 4 to 8, roughly, depending on the unit design, the feed, etc. And as you can see in this plot, you have advantage in terms of DO yield or quality by increasing the solvent to oil ratio if you keep the other variables same. And of course, I mean, there is a small penalty in terms of incremental operating costs because of the higher solvent ratio, meaning a higher solvent circulation rate, higher pumping, and the utility cost. But it's a marginal. And if you look at the real live example in the commercial unit, how this can be leveraged, you have a unit which is designed for 5 solvent to oil ratio, but to increase the DO yield for the downstream unit, if you have some fat in the unit, or if you have some extra margin to increase the solvent circulation, just by increasing the circulation from 5 to 8, this unit was able to lift 5 additional % of DAO for the unit with a very minor bump in the utility cost. But for a 50,000 barrels per day unit, 5% extra DAO is huge, and also translates into big number for the gross margin for the unit as well as the overall refinery. Okay, so we saw in the earlier slides, and we learned that extractor is the heart of the process, right? So, and extractor design very strongly impacts the CapEx and OpEx of the plant. So let us look at a little bit more in depth about the extractor design and how it improves the performance. So the simple principle, as we saw behind in the extractor, is the separation efficiency. which is based on settling theory. If you recall our mass transfer textbook back in the day, God knows when. But anyway, so separation efficiency increases with solvent to oil ratio, like we saw, changes with density, viscosity, and other process feed parameters. Of course, the vessel size, which is nothing but the residence time, right? And also the separation stages. So this is all impacts the separation efficiency. And in simpler terms, we know the efficiency of the separation is a big difference between the packing and the mechanical internals. So there has been a huge development and improvement from a traditional separation mixing, right? I mean, just when you are doing mixing with a simple mechanical stirring and just contact time, your efficiency of separation is not that great. But then you have a lot of updates and technology improvements with a different shape and size and material in the packing, which is great for improving the separation efficiency and mass transfer rate, etc. So at high level, you are looking some way in the extractor, some way to provide a contact time and a better separation efficiency for both the raffinate as well as the extract phases, which can be done through simple contact or can be done with the packing. So let's look at the different designs. So this is, of course, when we commercialized the process in 60s, the original designs for the SDA unit were with this old generation, original extractor internals. That was back in the day. This was the traditional internals. You can see on the left is one of the original ones, rotating disc contactors, RDC. The philosophy and principles is very simple. By utilizing the fluid energy externally, you want to create turbulence and in turn improve the separation and mass transfer rate. And as you can see, there are so many stages, just like a traditional distillation column. And remembering the McCabe-Thiele diagram for the separation efficiency for various stages, it applies also for the extraction efficiency. So multi-stage design plus the reflux ensures the excellence contacting and the interface. And it provided a good separator efficiency in those days. But obviously, it had little higher maintenance due to the motor and the seal and all the typical rotating equipment reliability stuff. Also, many units were designed with another type of internals in 70s through 90s. I believe, which were called parallel inceptor plates, PIPs, as you can see on the right. And again, this is to provide a higher surface area for the contact time. As you can see, so many plates are closely spaced and stacked on top of each other. But there was some ingenuity to the design. There was a lot actually for that technology. It is very, very clever. In fact, if you see, the plates are sloped to allow the pitch slurry to allow the pitch to run off to the lower, longitudinal edge of the each plate. So the separation efficiency was not that bad actually. And this both generation of internals had very good commercial results because so many units back in the day designed with this. And in fact, still operating with this old internals. And of course, we are working with many of our customers, and we encourage the customers to revamp the units with this old generation internals and replacing with the packing, high efficiency packing for the revamp to improve the efficiency, to improve the quality, as well as increase the feed rate to the plant, etc. Because for obvious reasons, this for the mass transfer limitation, there was limitation in terms of the capacity and size for the generation of internals. So coming back to the old generation to how we came up with this new generation, which is currently offered by our joint UOP SDA Technology. So the biggest technology development in the SDA overall is the use of structured packing in the extractor. As I mentioned, there is so much improvement in the size, shape, and void fraction and the material, etc., to improve the separation efficiency, surface area, etc. So in 90s, we were investigating the structured packing, and it suggested it offers a similar performance at a lower cost and higher capacity. So we worked with structured packing vendors to develop the counter current structured packing extractor, which minimize the entrainment of the contaminants, right? And ultimately, we saw very promising results, and we commercialized this structured packing. And both the packing and the proprietary distributors in the extractor, which permitted, combination of both, permitted the superficial velocities in the vessel very high. And when you can do it a high superficial and throughput, superficial velocity, you can achieve the same efficiency for the higher feed rates. And so we could able to design a single train extractor for a huge capacity, about 50,000 barrels per day. And in the early 2000s, early part of the century, when we commercialized this and offered it to our Japanese customer, Kyushu Oil, they selected this option for the first commercial offering over our competitor based on this design. And after that, the first commercial offering in early 2000, it just took off from there. So this was the biggest improvement in the technology, but there are many technology areas in SDA which are getting focus for improvement and advancement, right? For example, some of the focus areas are the heat integration and flow scheme improvements for CapEx and OpEx reduction, the reliability improvement, etc. But some of the initiatives have successful and have been implemented recently is the SDA integration with other conversion units and optimize the SDA design for those integration. So that has been very successful in recent times. And that is actually one of the main reasons why SDA has gained popularity, right? One example is to integrate SDA with ebullited bed resid hydrocracker and optimizing the SDA for that particular objective. If you know or have some knowledge about the ebullited bed resid hydrocracker, it is the technology has been commercialized for a long time, but it had limitations in terms of achieving conversion, higher conversion for reliable time. I mean, it can achieve conversion, but with a reliable operation for a long time, and also with a reasonable catalyst life, because there is a significant expense of the catalyst in an ebullited bed for the catalyst life and also the makeup rate, etc. So it was a big driver to improve that, the conversion rate reliably. And by integrating the SDA in ebullited bed hydrocrackers between the first stage hydrocracker reactor and the second stage reactor, we were able to improve the conversion by about 20-25%. So from 60 to 65% baseline conversion to 80 to 85% conversion, which is huge in the current environment because of IMO regulations, lower refining margin, etc. So there are multiple benefits because of this. Also, we have commercialized the pitch utilization and pitch gasification to generate steam and power. So SDA has been proven, SDA pitch has been proven for that application as well, which is also a big deal to improve the energy efficiency as well as to have a valuable outlet for the low quality products like SDA pitch and getting a good return. We are also working on the SDA commercialization for the Canadian bitumen feed. So all of you know that Canadian bitumen typically operates with a delayed coker or ebullited bed hydrocrackers to produce synthetic crude. But obviously the capital cost for the delayed coker is huge for these plants, and carbon footprint is also huge. So Canadian customers, of course, are focused on improving that part, and we are working for the SDA commercialization to use the SDA to produce the syn crude. So just at a high level to look at the overall SDA product routing, and of course, we both partners, Wood and our partner UOP, brings the full complement of know-how and the technology expertise for SDA, and also the integration technologies like downstream hydroprocessing unit or FCC unit to optimize the whole complex and improve the NPV of the whole project. We saw that the SDA is a selective separation which separates the residue into DO, which has high quality components, and the bulk of the contaminants goes into the pitch, right? Which results in shifting the better molecules to the catalytic based conversion process like FCC and hydrocracker for DAO. So we design this integrated units for optimization of the product value, and SDA is obviously optimized for the optimum DO quality going to these units. At the same time, the resin and pitch, which is optimized and better suited for the thermal conversion product or thermal conversion units, are suitable for thermal unit. We have designed these breakers. It obviously goes into the asphalt production. And as I mentioned, is also we have integrated with the gasification units for power and steam production. So there are a lot of various options, and you can clearly see the inherent flexibility of the SDA with a lot of other units within the refinery. If you look at the common outlets for the DO processing are the catalytic units like FCC and hydrocrackers, which have limitation in terms of feed contaminants. So very careful attention is needed for the SDA design. For example, nitrogen is an issue because of its inhibition function and neutralizing effect on the acid function of the zeolite catalyst. It doesn't matter whether it's zeolite or alumina, both have that same effect. Sulfur has a minor effect on the deactivating mechanism, and also just a higher overall sulfur load on the recovery units. Majority of the metals also a significant catalytic impact because of pore mouth plugging and also damaging the catalyst skeleton. CCR and asphaltenes also deposit the coke and irreversibly shorten the catalyst life. If we look at and evaluate the residue conversion economics and compare SDA relative to other conversion popular technologies like delayed coking, obviously is the most common one, you can see that the SDA holds up very well and perform well standalone, and even better when it is integrated with the delayed coking. And this is, of course, a very popular option, which I talked about in the last presentation a month back, or we will also talk about it, the integration in the future presentations, which are going to take place every month. So there is, when you look at it at a high level, obviously the gross margin for SDA is a little bit lower than coking because of the higher, the pitch production. But of course, integrated with the units improves significantly, both the payback period and the NPV. For the technology advancement we were talking about, one other aspect I would like to highlight is the continuous improvement in technology. And not just for our technology improvement, but also helping the customer verifying the yields and qualities for their feeds. And we are the only licensor who has access to our pilot plants, both batch and continuous plants. And again, these plants are used very efficiently in combination of other pilot plants like cokers and disc breakers to optimize the overall residue complex. And the pilot plants are fully capable of not just doing the product characterization and product properties, but also fractionation and blending of the various feed components to determine the reactivity for each component separately, because as we all know, the resid fractions of different crude origins have a significant different reactivity, and it impacts on SDA, the yield quality balance, and also changes the yield significantly for other thermal conversion units as well, like delayed coking and the thermal cracking or visc breaking, etc. Looking at the commercial experience, how this Foster-Wheeler wood UOP joint technology has been applied through this period. As you can see, we have been market leader in all the technologies we license in heavy oil area, which is demonstrated by this third-party independent data. And when you look at the SDA, we have licensed more than 50 commercial units from the very first one in 60s. And to this date, we license more than 50% of the competitive projects globally. This kind of market acceptance also shows our technology advancements and also the customer values it brings in terms of not just CapEx and OpEx, but also the reliability, safety, which are also very important part of the technology selection. I think we are almost getting at the end of our time slot. So before we do the question and answer, I just wanted to summarize the whole discussion. And I hope that this has enlightened you as to the opportunities that SDA may provide in your refinery and can unlock the opportunity for improvement. If you are looking at a new or a revamp of the residue conversion complex, I would like to reiterate, it is best done by considering the solvent deasphalting SDA and evaluating thoroughly in terms of not just the yields, but overall economics, product flexibility, and also the environmental impact. SDA is a key lever to fully optimize the processing scheme for the residue complex because of what we saw, the inherent flexibility and very low capital cost. And I cannot stress enough how reliable and simple it is with a very low carbon and environmental footprint relative to the other residue conversion units. Having said that, I would like to really thank you, all of you, for giving me an opportunity to talk today. And now I would like to answer any questions you may have for next 5 minutes. And of course, I will try to answer the questions in the box. And the questions which are left, I will get back to you individually with responses in next few days. Thank you so much, Becky. Thank you so much, everyone. Thank you, Becky.
Okay, Hemendra, can you see the chat box?
Yes, I'm just opening it. Okay, so yes, so the first question is the mixed solvents, about the mixed solvent for the SDA. How efficient are the mixed solvents? And to answer that question, it depends. Just like we saw, there are a lot of the factors and variables affects the selection of the solvent for the SDA process. And I think your point is very much valid, is when we go from, so the most three typical solvents are C3 to C5, but it's not just the pure solvent which is used, but majority of the commercial units are designed with the mixed solvent. And there has been many applications by blending C3, ISO C4, normal C4, and C5, all different solvents together and successfully operated. And obviously, the idea for mixing the solvent is pretty much the same philosophy what we talked about, is the consideration of the feed quality, feed contaminants, and the compromise between the DO quality and the yield expectations for the objective for a given solvent. So recall that the plot we have seen for the DO yield and quality, and of course, like I said, the maximum SDA DO lift is dependent on the CN insoluble for that solvent, and N refers to the carbon number of the solvent, which is different for each solvent, like C3, C4, and when you mix ISO C4 with C3 or ISO C4 with pentane, that number changes. And that is a key to decide that. So I hope that answers your question, that that is how the philosophy of the design and selection of the solvent for the different commercial units. Now, let me go to another question. What is the minimum and optimum temperature differences between the top and the bottom of the extractor with the pentane solvent? In Chivild, if you are in a good quality, I'm just reading the question. If you were in the good quality of metals and sulfur, but have asphaltenes in DO, what parameters should we optimize or change? Does softening point of the pitch play a limitation role in the operation temperature? That's a great question, because as we saw in the optimization of the different contaminants between the sulfur, the metals, and the asphaltenes in DO, we saw sulfur is not a huge issue for the SDA most of the time. But there is a different correlation to the asphaltene and the metals with the separation efficiency, and it is non-linear. But typically, directionally, the asphaltene and the metals go hand in hand. And that's exactly where the solvent selection comes into the picture. Like I mentioned earlier, for one or another, if you are getting a required specification for metal and not the CCR, utilizing a solvent or selecting a solvent, not just a single solvent, but by a mix of solvent, will help you getting over that issue in meeting the metal specification and not achieving the CCR quality, or vice versa in that case. So of course, and you can utilize the lever of the temperature and the solvent ratio to improve the separation and get the better quality like we discussed. But the temperature obviously has a limited window because it is optimized for that particular solvent, and the critical point is another limitation to that window. But the type of the solvent, the making changes, and also the solvent ratio changes is going to be a very key. And it can be done in operating unit by making those changes, all evaluating a small revamp changes for the operating unit to do that. So for this question, I would request the particular person to email me directly with some of the information about the metals and CCR, etc., for the feed quality and what exactly the specification issue, etc. And we can review it ourselves by simulation, and we can give you a good idea about what to do with very, very small changes in the operation. And another aspect of this question is softening point. So this is, of course, is a very good question, because softening point of the pitch is also directly related with the operating temperature. Not just the operating temperature, but it is also related with the type of the solvent which is used in the process. And typically, directionally, when you go to the heavier solvent from C3 to C4 to C5 to C6, you have higher and higher softening point of the pitch you can live with. But it also brings up a safety and reliability issues, and also brings up other questions also. What is the final disposition of the pitch? What are you doing with the pitch? Whether you are producing a liquid pitch or you can live with the solid pitch and do the flaking or something like that. So again, it depends on so many other parameters for the ultimate disposition of the pitch and the other parameters. So again, if you want us to look at a little bit more depth, or if you can supply me with some more information, I'll be more than happy to answer that question. And it seems like we are almost out of our time, or we are out of time. So what I'll be doing is I will have access to all the questions and the people who have asked the questions. So I will respond in next few days to individually for these questions. And please feel free to let me know with the detailed information so that I can respond to you for your particular application. Thank you so much.